In this next section, we're going to be looking at conservation of linear momentum for a system of particles. Now, if you recall, we had that impulse, we had our conservation of our linear momentum equation, which was basically mv1 plus sum of the integral forces that act on it is going to equal your final momentum, right? And this was our momentum. And this was our momentum. Well, this whole thing. Just that. This one. Momentum. And then this in here is the impulse. Alright. Now, if you look at the conservation of linear momentum, so conservation of linear momentum says that the sum of the impulses of FDT is going to be 0. Now, this works when you look at the system, at the entire system. So when you're thinking conservation of energy, technically, well, you lose energy in heat and sound, but if you look at the whole system, heat and sound are still in the system, so you haven't actually lost them. So that's kind of what we're looking at. Whenever you're looking at the full picture, you can assume that we would have that mv1 of the entire system would equal to mv2 of the entire system. So usually, whenever you're looking at this, you're like, well, the sum of all the masses and the sum of all the velocities. But just in general, this applies to the whole system. And then if you're just going to look at a part of the system, then that's when you would apply this up here. So where this is coming from is the idea that so velocity doesn't change if there are no external impulses acting on it. Okay, so now when we're talking about impulses, just to kind of give you an idea, usually when we're looking at this, we're looking at, here's the ball, it's going this way, and bam, it's hit by a tennis racket, and now it's going this way. Okay, so when we're talking about impulses, what we're talking about hits, strikes. An example they give in your book is, if you've got a hammer hitting this, nail, you've got the weight of the nail, right? Now, but that is a non-impulsive force because, the way I like to think about it is, before here, gravity's there, and after here, gravity's there. But the pounding of the hammer on the nail, well, that's an impulsive force, right? Because it only happens once. So if I was going to look at this equation here, if I was just looking at the nail here, I would say, well, I have gravity over here, and I have gravity over here, but I only have the, whatever you call it, pounding, the strike. The strike is just before, and it only happens like, something's originally happening, something's finally happening, and this strike only happens right in the middle of when we're before we measure and after we measure, whereas gravity happens the whole time. Gravity is this little constant throughout the system. Gravity goes this way and this way. If you're thinking about time, it's not like the fanciest way of thinking about it, but it's the way that always makes sense to me, is that, gravity takes place throughout the entire event, but the strike is just like, bam, it's just right there. So that's considered an impulsive force because it's the thing that's actually changing. Gravity was still impacting me when I had this velocity, so obviously, I've already taken that into account. Gravity's still going to be here at the end, so I don't have to take into account. What I need to take into account is the impulsive forces, or that actual strike. Okay, so a couple of strategies when you're solving these is to remember that if I want to find the average force over a period of time, I could look at the sum of those forces averaged over time. Okay, so make sure you have this, because when they ask for average forces, you might say, "Oh, no, I have an equation for that." Well, it really just means, the sum of the forces divided by the time that you're looking at. So, for example, in this, you're going to end up with MV2 minus MV1. I keep forgetting to do that. And here we go. How's that? Is that better? Over delta T. And that's going to be our F average. Okay. So, don't really memorize this equation specifically. Just remember, if I'm looking for average force, I want to find all my forces, divide by the amount of time that we're looking at. And so that's one thing that you want to consider. The last thing that you want to make sure is that, remember that you apply MV1 equals MV2 to the system. And then, because usually what you have, usually V1. Usually know where you start, and you're trying to figure out, well, where did I end up? So if you just started looking at a classic example that's in your book is, two trains are colliding. What is their velocity after, and what is the force between them? Well, if you wanted to know the force between them, if you were just looking at the first car, without getting too detailed, if you only know this, you have two unknowns. So the way that you solve it is you look at the system, you find the final velocity of the system, and then you can go in here, and then you would have this, and now this is your only unknown. Okay, so that's going to be the kind of strategy that you're going to apply throughout this section.